Hello, welcome to my presentation video on protective earthing conductors. My name is Martin Lavachka, and in this video I'm going to talk about connection and choice, conductor sizing, protective conductor between NV-LV transformer and the main low voltage switchboard, and equipotential conductor. Protective conductors provide the bonding connection between all exposed and extraneous conductive parts of an installation to create the main equipotential bonding system. These conductors conduct fault current due to the insulation failure to the earth neutral of the source. PE conductors are connected to the main earthing terminal of the installation. The main earthing terminal is connected to the earthing electrode by the earthing conductor. PE conductor must be insulated and colored yellow and green and protected against mechanical and chemical damage. In IT and TN earth schemes, it is strongly recommended that PE conductors should be installed nearby as the live cables of the related circuit. This arrangement ensures the minimum possible inductive reactance in the earth fault current carrying circuits. It should be noted that this arrangement is provided by construction for busbar trunking systems. PE conductor must not include any means of breaking the continuity of the circuit, connect exposed conductive parts individually to the main PE conductor, and have an individual terminal on common earthing bars in distribution panels. The diagram shows how poor connection in series arrangement will leave all downstream appliances unprotected. The connection should be in parallel. In the TT scheme, the PE conductor does not necessarily have to be installed near the live conductors of the corresponding circuit, since high values of earth fault current are not needed to operate the RCD type of protection used in TT installations. In the IT and TN schemes, the PE or PEN conductor is previously noted, must be installed as close as possible to the corresponding live conductors of the circuit, and no ferromagnetic material must be interposed between them. A PEN conductor must always be connected directly to the earth terminal of an appliance, with a looped connection from the earth terminal to the neutral terminal of the appliance. In the TN-C scheme, the protection function of a PEN conductor has priority, so all rules governing PE conductors apply strictly to PEN conductors. During the transition from TNC scheme to the TNS scheme, the PE conductor for the installation is connected to the PEN terminal or bar, generally at the origin of the installation. Downstream of the point of separation, no PE conductor can be connected to the neutral conductor. Materials of the kind mentioned below in the table can be used for PE conductors provided that the conditions mentioned in the last column are satisfied. Conductor sizing. The table below is based on IEC 60364-5-54. This table provides two methods of determining the appropriate CSA for both PE and PEM conductors. The first method is adiabatic. This method, while being economically and assuring protection of the conductor against overheating, leads to small CSAs compared to those of the corresponding circuit phase conductors. The result is sometimes incompatible with the necessity in IT and TN schemes to minimize the impedance of the circuit earth fault loop to ensure positive operation by instantaneous overcurrent tripping devices. This method is used in practice therefore for TT installations and for dimensioning an earthing conductor. The second method is the simplified method, which is based on PE conductor sizes being related to those of the corresponding circuit phase conductors, assuming that the same conductor material is used in each case. The neutral cannot be used as pen conductor unless its CSA is equal to or greater than 10 mm squared for the copper conductor or 60 mm for the aluminum conductor. Moreover, a pen conductor is not allowed in a flexible cable. Since the pen conductor functions also as a neutral conductor, its CSA cannot in any case be less than that necessary for the neutral. Furthermore, the protection of the neutral conductor must be assured by the protective devices provided for phase conductor protection. Values of factor K to be used in the formula. These values are identical in several nation standards, and the temperature rise ranges, together with factor K values and the upper temperature limits for the different classes of insulation, correspond with those published in IEC 603-64-5-54 Annex A. The data presented in the table are those most commonly needed for LV installation design. Protective conductor between MV-LV transformer and the main low voltage switchboard, all phase and neutral conductors upstream of the main incoming circuit breaker controlling and protecting the MLVS are protected against short circuit and fault currents by devices at the MV side of the transformer. The conductors in question, together with the PE conductor, must be dimensioned accordingly. Recommended conductor sizes for bare and insulated PE conductors from the transformer neutral point are shown in figure G61 are indicated below in figure G62. The KVA rating to consider is the sum of all transformers connected to the MLVS. The table indicates the CSA of the conductors in millimeters squared according to the nominal rating of the MV-LV transformers in kVA, the fault current clearance time by the MV protective devices in seconds, and the kinds of insulation and conductor materials. If the MV protection is by fuses, then use the 0.2 second columns. In IT schemes, If an overvoltage protection device is installed, the conductors for connection of the device should also be dimensioned in the same way as they described above for PE conductors. The main equipotential conductor must in general have a CSA at least equal to half of that of the largest PE conductor, but in no case need to exceed 25 mm for the copper conductor or 35 mm for aluminum conductor, while its minimum CSA is 6 mm for copper or 10 mm for aluminum conductor. A supplementary equipotential conductor allows an exposed conductive part that is remote from the nearest main equipotential conductor to be connected to a local protective conductor. Its CSA must be at least half of that of the protective conductor to which it is connected. If it connects two exposed conductive parts, its CSA must be at least equal to that of the smaller of the two PE conductors. Equipotential conductors, which are not incorporated in a cable, should be protected mechanically by conduits, ducting, etc. wherever possible. Other important uses for supplementary equipotential conductors concern the reduction of the earth fault loop impedance, particularly for fault protection schemes in TN or IT earth installations, and in special occasions with increased electrical risk. We come to the end of this presentation. Thanks for watching.